Hello all. In this video, I'll be demonstrating how to develop Verilog code for 8 is to 1 multiplexer in behavioral description. So, as all you know that the Verilog behavioral description is considered as one of the highest level of abstraction, where if you know your digital device or digital system information in terms of its behavioral characteristics, which can be implemented because much flexible behavioral constructs are available in Verilog behavioral description style. So let us look one such construct, that is using case statement using multi-way branching, how to develop Verilog code for 8 is to 1 multiplexer. That we're going to look in this particular experiment. So, as you all know, that 8 is to 1 multiplexer is a combinational logic circuit which consists 8 inputs, 8 data lines or 8 data inputs, and one output along with 3 selection inputs. Okay, these are all called data inputs, and these 3 inputs are called selection input. So, for every 2 power n number of data line, there should be n number of selection line. Okay, this is the relation between the number of data lines in the multiplexer to the number of selection line. But irrespective of any number of input line, there should be only one output terminal for 8 is to 1 multiplexer. For this design, we also incorporated one enable pin, which is active low. So, looking into the characteristics of 8 is to 1 multiplexer, look at the table, truth table, which specify the nature of 8 is to 1 multiplexer. Suppose if enable is 0, then we can say this particular system is activated, and if enable is 1, then irrespective of any selection line or any data line, let us consider the output will be in high impedance state. Okay, so it is active low enable. Therefore, I kept enable line as activate by making it as 0 for different possible combination. So if my combination of selection lines are 0 0 0, I naught line will be picked as output. Okay, why is nothing but output. Output will pick I naught line. So that means whatever the input we are passing through I naught line will pass as the output. Okay, that means if I naught line is selected by making S2 S1 S naught as 0 0 0, whatever the value I am passing or whatever the value which acquired at I naught line will be appearing as output. For example, if the I naught line is 0, output is also 0, or otherwise if I naught line is 1, then output also remains 1, or otherwise if it is unknown X, then output also remains unknown, or else if I naught is at I impedance state, output also remains high impedance state. Okay, therefore output Y just switches to the I naught line. So that is going to apply. That means this particular case is going to be similar for rest of the possible combination of selection line. That means if selection line is 0 1 0, I2 line will be picked. If it is 0 1 1, I3 line will be picked, so on and so forth. If it is 1 1 1, selection lines are 1 1 1, then I7th line is going to pick. Okay, this is the operation of multiplexer. And if my enable line is 1, suppose if I deactivate the 8 is to 1 multiplexer, irrespective of any combination of selection line, let the output will be high impedance state. Okay, so this is the design specification. Let us try to develop a Verilog code for the same. So let me create a project. I create a new project. Uh, Project name I'll keep it as Mux, and I'll route to a specific directory. Then click next, create a new source, new Verilog module. Give the file name as mux underscore 821. Please don't start your identifier with character. Always identifier should be start with either alphabet or underscore. Underscore is allowed, but usually we will always start the identifier with character. Make sure that the same Verilog module is added to the project. Click next and specify the ports here. Okay. Now look at your design. Let me look the design. With respect to design, let us try to explain the program. Let me try to explain the program. Okay. File, a new project. Project name is Nux. Click next. Next. New source. Select Verilog module. Nux underscore 821. Click next. Specify the ports. Here I have the following ports. Look at the presentation. So I have eight input, that is input data lines. So therefore I'll instead of taking one input of eight input of single bit size or eight scalar input, I'll take one input I, which is of vector type. Okay, therefore I'll make MSB as 7 and LSB as 0. So instead of taking 8 scalar inputs, 1 bit input, I'll going to consider one input I, which is of size 8 bit. And I have one more input called yes, okay, selection input, which is actually three independent line, or otherwise I can take it as a three scalar inputs. Instead here I am making it as vector. So my MSB is 2, most significant bit is 2 and least significant bit is 0, and I have output y, which is scalar 1 bit output. So these are the input and output port specifications for this particular design. Okay, instead of just to make program easy, rather than taking scalar inputs, I make the input as vectors, both I and s. Data and selection lines, I made it as vectors. Okay, click and change the direction of y as output. Click next, and the summaries will be visualized here. Finish. Yes. Next, next, finish. The source file got created. Uh, Very importantly, since I am writing a behavioral description, whichever the variable which is appearing to be LHS side of the expression in always block or initial block should be modified as register. Therefore, the y, it is an output variable, obviously which expected to be appear at the LHS side. I'll modify it as register. So this is how to modify the variable y since it is appearing at LHS side of the expression in the always or initial block, or it is a which is going to be right within the behavioral construct. Therefore, I am modifying the output as register. This is the rules. No additional variables are required. So directly I'll start with always block. Okay, always at event control. I'll specify the port sensitivity parameters list here. So here all the inputs supposed to be a sensitivity parameters, that is I and S, both are sensitivity parameters. So I'll mention both I comma S, or we can also specify I or S. Then I'll begin the always block. Have more than one statement in the always block or initial block should be blocked by using, or should be grouped by using begin and end. Begin. Now first in my construct, this particular design should verify what is the condition of enable, and if enable is 1, without testing for any possible combination of the input, output should be high impedance. Therefore I am performing that. I am testing the condition of enable. So I'll use if statement. I'll test if enable is equals to 1. So here I have missed the declaration of the input enable. So I'll declare that also here, input enable. Okay, separate by comma. I'll test if enable is 1. So obviously my output should be high impedance. Therefore I'll make y is equals to 1 tick z. I'll assign output as high impedance state if enable is 1 and with semicolon. Else, if enable is 0, then by default my system is supposed to be activated. So I'll use multi-way branching, that is case statement. Okay. Else case, here testing element is selection line. So I'll include a test object as yes. So I list all the possible combination for the selection line. So selection line has this following combination. Okay. You can look at the presentation at the LHS side. selection line, since it is 3-bit selection line, which has the combination from 000 to 111, I'll include all the possible combination. So if my selection line is 3-bit 000, then I'll assign output y is equals to first line. So first line means I zeroth line. Therefore, since it is a vector, I'll access the bit of the vector I of 0. So always the bit of the vectors or part of the vectors should be represented in square bracket and with semicolon. Likewise, I'll test for next possible case. If it is not true, I'm going to test for some other alternative cases. That is, if selection is 3 tick bit 001, make my output y as I of 1. Okay, so on and so forth. So now look at the program. So the always block is sensitive to three parameters. Okay, the one is input data line input I, selection line S, and also enable uh, input En. And if any signal variation in any of these three, the always block is going to be executed. And if enable is 1, the output will be remains at high impedance state. Otherwise, it tests the different possible combinations for selection line. And if it is 000, y acquires I of 0th line output. Okay. And if it is 001, output will be acquiring first line of the data, and so on and so forth. And if your selection line does not match to any of this specified combination, then the default statement is going to execute. So if your selection line is not matching to any of these 8 possible combinations, then the output will be remain 0. Look at you must observe the different constructs supporting in case. So case, default, and end case are the constructs supported in multi-way branching in behavioral style of Verilog. Okay, and end case is should be a single word, uh, and default should be used in association with case only. Okay, default will not support outside, so you must use in along with case. The default should use along with case statement. Always it is recommended to use default statement whenever you use multi-way branching like case. Okay, now save, and let us check the syntax for the same. Okay, it is error free, and let us synthesize. So successfully it is synthesized. So let us test the functionality of this design using a Verilog test bench module. So I'll create a new source. I'll select test bench waveform. Uh, my test bench waveform is mux underscore test. So click next and make sure that as appropriate design block is selected. Here my Verilog design block is mux 821. Click next. Finish. So since it is a combinational type of device, I'll select combinational input. Finish. Now, these are all the input lines, enable, and I, S are the input line, and Y is the output line. Okay. Now I'll make enable 0 initially, and I'll feed the different possible combination of input and selection line. Okay. First I'll make selection line. Since my selection line have fixed pattern, that is 000 to 111, I'll right click from 100 to 200 nanosecond. In that specific time period, I'll right click and I'll set the value. Select pattern wizard. So pattern type is count up type because my sequence is starting from 000 and ending at 111. Total I have 8 different combinations, therefore I'm taking 8. Let me keep my values in binary. Initial value is 0 and last terminal value is 111. For each value, I'll increment, for each sequence, I'll increment by 1. Click OK. So therefore, all the sequence going to be, all the possible combinations for the selection lines are selected here. So here it is displaying hexa. If you want, right click and tick binary, so that these input values will be represented or displayed in binary format. Okay. Now I'll set my data lines. So for my understanding, I'll make I not 0 as 1. uh, when my selection n is 1, it is not essentially to be 1. Just I'm testing uh, possibilities by making all data lines are 1 for that specific combination. And I'll make I1 1 for combination 1, likewise I2 1, I3 1, so on and so forth. So I'll keep I6 as 0 and I7 1, I7 1. Okay, right. And at last for this combination, I'll make uh, enable 1. Okay, so here enable is here. I'll make enable 1 for the last combination. So look at here, I fixed all the possible combination for selection line. Whereas for a particular selection line, I make appropriate data line as 1, so that I can observe clearly whether the particular multiplexer choosing an appropriate input line or not. For last combination, I randomly made enable as 1. Okay, I'll save this test bench waveform. Now go to process window and source window, perform behavioral simulation, select the test bench waveform what you created, then perform simulate behavior modeling. Okay, perform the simulation. So it represents the result here. Okay, now let me represent my output at last and replace that. I'll make enable 1 here. Okay, I'll elaborate the input and represent my selection line in binary. Look at area, if the selection line is 0 0 0. Okay, so if selection line is 0 0 0, so multiplexer should pick I naught line. Look at the I naught line for this instance, I is 1. Okay, I of 0 having the value logic 1, therefore output also remains at logic 1. And similarly, I am going to test my result for a combination of selection line 0 0 1. I'll keep the marker here. So selection line is 0 0 1, so it has to pick the first line of the data line, first input line from the multiplexer. So I1 has logic 1, therefore output also remains 1. So on and so forth, you can test for the different combinations here. Now for the selection line 6, okay, uh, here it is 5, and for selection line 6, it is sixth selection line. That means combination of selection line is 1 1 0, where I sixth value is 0, therefore output also remain 0. And in this particular case where I kept my marker, enable is 1, therefore irrespective of the selection line and data line, output will be remains at high impedance state. Okay, so this functionality can be verified. Thank you for watching this video.